Hey everybody, and welcome back. So this is going to be the first lesson in Unit 4. We are entering into rational functions, and I'll explain what rational function is in a couple of minutes, but just be aware that this is one of the units that's going to be a little bit more pared down compared to some of our other ones. So there may be some things missing. You're like, oh, we normally did that in other lessons for different functions, but we're not doing it in this one. Totally normal, just know that we've cut it out probably. All right, you're going to find this is a very short lesson because there's a lot of new vocabulary, which I want you to really focus on getting a grip on. So new words that are coming in, make sure you know what they mean and how to use them in context. All right, so today's goal is factor polynomials. You've done that before in rational functions. Okay, that's new, but not too bad. To cancel out common factors, we should be able to do that. Identify excluded values in rational functions. So new word, excluded values, what does that mean? And then how do I find them? Those are our essential questions. All right, so in our last video, we wrapped up Unit 3. We solved for complex zeros and polynomials using the synthetic division tables from the rational root theorem. And then we also wrote equations of polynomials when given the zeros. So we knew what the zeros were, and we were asked to write the polynomial, and that also included complex zeros. So radicals and imaginary numbers getting a special treatment. Okay, so rational expressions, what is it? It's just basically two polynomials that are being divided. So remember, polynomial just means many terms. So you've got a many-termed expression on top and a many-termed expression on the bottom, and that is a rational expression. So a rational number, remember, is any number that can be expressed as a fraction. A rational polynomial, same thing. So just two examples here. Now it's not solving. So this looks like what we did in the last unit with solving polynomials. We're not being asked to solve them here. We're being asked for other things like graphing them, or what is the value of a coordinate at this given x value. So different to what we're being asked for here. Now you may still be asked to solve them to find out what are the zeros, but you may also not be asked that. So be aware that there's going to be a difference here. Let's just take a look at their graphs because they are quite unique in terms of how they look. So here's that first one. So very quickly we notice, oh, this graph is got two parts to it. It's split. And I don't know if you can quite see it. I wish I had a straight line tool on this, but there is essentially like an invisible wall running up here and running down. So it's basically a linear function. So you imagine that there was a straight line there. It got close to it, and then it just kind of hit this force field, and it had to bend up and avoid it. And it actually goes up to infinity and never touches that line. So it's approaching it. Same thing on the other side. It comes from negative infinity, approaching that x value, whatever it is, and then comes up to a point where it starts curving off and continuing that linear function again. So this invisible force field is an excluded value. It's a value of x that is not possible to have a solution for. Looking at the rational expression, can you see what that value might be? So what is a value for x that would make this fraction unable to be solved, or infinity, or undefined? So the idea here is that you cannot have a fraction over 0. So if you try and divide by 0, there's an infinite amount of nothing in anything, which is just a very fancy way of saying you can't divide by 0. So that means if x plus 5 equals 0, this whole fraction would equal infinity. So that means at x equals minus 5, the fraction would equal infinity. So at minus 5, so this invisible force field is at x equals minus 5, the function's not possible at that point. So it gets closer and closer and closer and closer to it, but it does not ever reach x equals minus 5. That is an excluded value. And then for the other one, the 1 over x squared minus 9, I just got to get rid of all my notations. Very different again. So for this one, can you see it? There are two excluded values. So there's one here, there's like that force field wall going up, down, and same thing on the other side. Now the reason why there's two is that in the top one, the denominator was linear. There was only one x value that was excluded. This one is a quadratic, and there are two possible values for x that would result in the denominator being 0, which is why we have two of these vertical lines that cannot be approached. We call them asymptotes, by the way, and I'll give you the spelling for that in a second. So we're going to have to try and figure out where these excluded values are. That's going to be our task. So excluded values for the two, we've got asymptotes, which are those invisible walls that basically a function approaches but can never touch. And then I want to give you another example as well. If you saw this rational function, so x plus 2 times x plus 3 divided by x plus 3, you would immediately say, oh, well, this is easy. Like, there's an x plus 3 on top and bottom. I can just cancel this out. And the answer is x plus 2, right? Well, yes, if we were going to try and solve it. However, for our original function, x plus 3 is a denominator and it was canceled. There's going to be one point here which does not work for us. And this is going to be called, so when you can cancel out a factor like this, you end up with a graph that looks like this. So it's still that linear function of x plus 2, but if you hover over x equals -3, there is one point, just one, that has no solution. It's undefined. So our denominator in this case was x plus 3. So that means if x is equal to -3, the denominator would be 0, the whole thing would be equal to infinity. So we have one excluded value in this case, and that is called a hole. So our excluded values are going to include asymptotes and holes. Asymptotes are lines which a function cannot cross. So it pretty much is like that invisible force field, that barrier, and the function avoids it. Holes are just one point that cannot be part of the solution. It's very important here to think about domain and range. So like when we look at the function that's currently up on the screen, the domain in our case here is no longer just -infinity to +infinity. It would go -infinity to -3 round parenthesis because it's not included, and then it would be a union with -3 to +infinity. So there is that break at -3. So the only one that's not included is x is not equal to -3. So that would be another way of writing your domain. Same thing for range. So our range, if it was -3, the y value should be -1, but it's excluded. So we would say the range goes from -infinity to -1 and -1 to +infinity. So again, just x is not equal to -1. That will be our range. So just keep an eye on that. That's a question you're going to be asked at some point, is what's the domain and range of the rational expression? And you're going to have to identify the asymptotes and the holes, and those are going to be excluded values, so they will not be part of the domain or the range. Okay, so let's do something a little bit more practical here. We're going to try and find holes and asymptotes. What are the excluded values? So we look at this and we say, oh, x minus 1. If x is equal to 1, that must be an excluded value. But the question is that an asymptote or is it a hole? If it's an asymptote, that means that there's no common factors between the numerator and the denominator. We're not going to cancel it out. If it's a hole, there is a common factor between the top and the bottom that we can cancel out, and that would make it a hole. So it would just be a break in the line as opposed to an entire value of x that it cannot approach. So we have to see, are there factors of the numerator that would also be divisible, or a factor of the denominator? So 1 minus x squared, you may recognize that. That is a perfect square, so 1 squared and x squared, so it's the difference of two squares. So we got 1 squared minus x squared. So remember, that's my a squared minus b squared. In factored form, that's a plus b times a minus b. So this would be 1 minus x, 1 plus. It's a bad plus. 1 plus x. So rewrite that top part in factored form, 1 minus x, 1 plus x, all over x minus 1. Now, it doesn't match anything perfectly at the moment. However, what would happen to this first one if I also factored out a -1. So if I said -1 is my greatest common factor. So I would have -1 taken out. So that would leave me with a -1 plus x times 1 plus x all over x minus 1. And -1 plus x is the exact same thing as x minus 1. So the x minus 1 part would cancel. So there is a hole in this graph. So we'd say there's a hole at x equals 1. And then what's left over is -1 times 1 plus x. So that would be what? -1 minus x. So you'd have a linear function with, so y equals minus x minus 1. So slope of -1, y-intercept of -1. But at x equals 1, there's going to be an undefined value, a hole. So if you were just looking at the linear function, you wouldn't even know that was there. But starting with our original rational function, we do know, okay, there is an excluded value at 1. It's going to be a hole as opposed to like that value it approaches. So the shape of the graph would be very different. You would just get the, so let's see, pass through -1, slope -1. So you would get something like this with that open circle as opposed to that kind of like barrier that would be going on. So it would come down, turn, and then come down and continue. So like it would look different depending on whether it was an asymptote or a hole. Okay, so that's pretty much it. We're going to do another example, and then you're going to try one on your own. All right, so we got x minus 1 over x squared plus 3x minus 4. Looking at the bottom one, it's a quadratic. Can we factor it? So x minus 1 is already a linear function. We can't factor it. But the bottom part, factors of -4 that add up to be 3. We've got x plus 4, x minus 1. So we would say, yep, there is a hole at x equals 1. And then we're left with 1 over x plus 4. Now, x plus 4 is still in the denominator, so we're not done yet. There's still a potential value of x that would result in 0, and that would be at x equals -4. So since it can't cancel, we would say there is also an asymptote at x equals -4. All right, let's let you guys take a shot at this on your own. So our excluded values are 1 and -4, but one of them is a hole, one of them is an asymptote. So you need to know what an excluded value is, and then you also need to be able to identify, is it a hole or is it an asymptote? So asymptotes are what's left over after everything's been canceled. Holes are any canceled factors, like what is the value of x that would make that factor 0. All right, your turn. Take a shot at it. Find the holes and the asymptotes of the given functions. There may not be both, there may only be one, but I want you to pause the video, try it out, and then see how you did. Okay, welcome back. So let's take a look at that first one. X squared plus 6x plus 5. In factored form, that will be x plus 5 times x plus 1 all over x plus 1. I just put it in parentheses so that's easier to see how it cancels. So we can cancel that x plus 1. We're left with x plus 5, but there is a hole at x equals -1. So -1, there was an excluded value. Looking at the original function, we can tell -1 is going to be excluded. We just didn't know if it was a hole or an asymptote. For the second one, they're both quadratic, so we're going to have to factor both of them. Top one, -21 factors would be 7 and -3. So x plus 7, x minus 3 over factors of -6, that would be -1, that would be -3 and +2. Okay, so the -3's cancel. So we've got x plus 7 over x plus 2 would be the simplified version, but there is a hole at x equals 3, and then there's still a value that could make this denominator 0. It would be at x equals -2. So we would say there is also going to be an asymptote at x equals -2. And I would encourage you guys to like pull up Desmos and take a look at what the graphs of these look like. It's very helpful, particularly in these types of functions, to just look at the graph and see what's going on there. Like, does it just look like nothing's happening, in which case there might be a hole in the graph, or is there a very clear invisible line that this graph refuses to touch? So that would be telling you, okay, you've got asymptotes going on here. So essential questions: what is an excluded value? It's basically a hole or an asymptote, a value that would result in the denominator of a rational expression being 0. How do I find them? You factor the numerator and the denominator down into linear terms, cancel anything that would cancel out, those are your holes, and then any value of x that would make the denominator 0 would be an asymptote. All right, so after this, you're going to complete the module. The independent practice is pretty small. It's only, I think, 5 questions. So we're starting nice and slow, starting easy. Make sure you know what your excluded values are, your asymptotes, and your holes, and how to find them. That's your real focus for this particular lesson.